Hello everyone and welcome to the second part of the tutorial on logistic regression implementation in Python by ThinkUponAI. So for a quick recap, in the first part we discussed how we could load the dataset into our environment and use the different methods which are available in the pandas library in order to gain some insights on the content of our dataset. Once we have some insights, then we moved on to the next section of data pre-processing where we modified our dataset in order to convert the problem into a binary classification problem suitable for our task. Then we used different type of plots in order to see the correlation between the data and identify the outliers that few of the columns had in the dataset. Once we have pre-processed the dataset, then we moved on to the next section where we prepared the training and test dataset for our model. So we used a train test split method where 70% of the dataset was being used for training the dataset and 30% was used for the test dataset. Once we have the dataset prepared, then we moved on to the next section where we created an instance of the logistic regression model where we fitted the model on to our training dataset. Then we used the .predict method in order to predict the quality values for the test dataset of our wine samples. These predicted values are then used in order to test the performance of our model. Now there are different performance metrics available in the sklearn library, but for our task we used accuracy as our performance matrix, where our model achieved an accuracy of 87.91%. Furthermore, we also looked upon the confusion matrix, which could also help us gain some more insights into the performance of our model. So this was all that we have discussed in the part 1 of the video. If you haven't watched the video till now, I would highly recommend you to go and watch that video before continuing on to the second part. Now if you're ready, let's jump into the notebook. Okay, so in this section of the notebook, we would be discussing the further improvements that we could do in order to improve the performance of our model. Now there are two parts to it. First, either we can improve the data set that we have, or we can improve our model by improving the hyperparameters that it contains. So in the first section, I would be discussing three techniques with you, which contains removing the suspected outliers, normalizing our data set, and doing feature selection. While in the last part, I would be discussing about the hyperparameter tuning for improving the model. So let's start with the first technique. So in the first technique, in order to remove outliers, we should first know what are outliers exactly. So outliers are any points in the dataset that are at an abnormal distance from other values in the random samples. Now in order to remove the outliers, we need to import some of the required libraries. So Plotly is the library which helps in data plotting and plotting the suspected outliers for us. So in order to facilitate that, I have created a custom function named outliers box, which intakes the data frame, which is the data set that we have, and the feature name for which we need to detect the outliers. So this function plots two traces, trace 0 and trace 1. So trace 0 plots a box plot with all the points that the column contains, while trace 1 plots the box plot with the suspected outliers. Now let us see it happening with the first column. So if I just run the function for the first column, you can see on the left hand side in the blue color, there are all the points in the column plotted here along with the box plot. While on the right hand side in the orange color, you would see the points which are plotted outside are the suspected outliers. So these are the points which are very far away from the distribution of the data points that we have in that particular column. So this box plot helps us visualize that distribution. So what it plots is, it plots the median line, which is here, and the quarter 1 and quarter 3 percentiles above and below it. So what are Q1, Q3 values is, so any value which is less than Q1. So here it is 7.1. So if a column contains values ranging from different minimum and maximum, so all the values which are less than 7.1 constitutes 25% of the data set. And all the values which are less than Q3, which is 9.2 here, constitutes 75% of the data set. Also, the difference between Q3 minus Q1 is also known as interquartile range, and this range is used to predict the outliers in the predefined formulas. So I'll show you how this formula works for this particular example. So if I say this, for this case, the interquartile range is 9.2 minus 7.1. So 2.1 is the interquartile range, and if I multiply it with 1.5 and add it to the Q3, which is 9.2, I'll get the upper fence of my box plot, which is 12.3, as you can see. So any points above these upper fence are will be categorized into suspected outliers. So based on this formula, these outliers are calculated. So once we have the function that calculates the outliers for us, I have created another function that removes these outliers based on this formula. So right now I have shown you that the interquartile range, which is Q3 minus Q1, is multiplied with 1.5 to add the step to the Q3 value. But in our case, I'll take 3 as the multiplication factor just to be on a safer side. So this function will remove the outliers, and then this function is called for each of the columns in our whole data set. So it will take some time, and if you see at the end of it, yes, so if you see at the end of it for the pH and sulfates here, the new data set with remove outliers has 1435 samples. So as you remember, the samples in the original data set were 1599, and this has been reduced to these number of samples. So all the difference is been removed as outliers. Now once we have our clean data set without any outliers, we just create another training and test data set along with that, and we train our model to see how it performs with the new data set. Now as you can see, the accuracy that we have achieved with the new data set is 88.86%. If you remember, for the past data with the outliers, the accuracy was 87.91%. And that's the improvement in the performance of our model. So that's a good news. Now, once we have removed the outliers and we have seen the effect of it, we can move on to the next section of data normalization. Now, in data normalization, first, why do we need normalization of our data set? If you see the content of our data set, the minimum and the maximum value that we have for each of the column is not same. So let's say, for example, fixed acidity, the wine has a minimum of acidity 4.6 and maximum of 15.9. While let's say the pH value ranges from 2.7 to 4. So you see the range of each of the values in the column is not same, and that could also affect the accuracy of our model. So in order to project all the values in a common range, we do data normalization. So in order to do data normalization in Python, first we need to import our method called min-max scalar from sklearn library. So it will normalize our data set using the dot fit transform method. So the input is given as all the x values, and the output is the normalized data set. So if I just run the cell and see what are the new values, you'll see all the values in our data set are now ranging between 0 and 1. So now if I train my model and check the performance with this new data set, we can observe that the achieved accuracy with this new data set is 90.72%, and which is again improved as compared to the previous technique that we used. So that's again a good news. Now moving on to the third section, which is the feature selection. In our whole data set, we have different features, and each feature contributes to the prediction of the quality of wine. But each of them do not contribute equally. Some of the features would have higher impact, while other features would not have much impact on the prediction. So the features which do not have much effect could be removed in order to avoid the redundant information from our dataset, because this redundant information could lead to overfitting our model onto the dataset, and which in further decreases the accuracy on the test dataset. So in order to do feature selection, there are different methods available. What we have done is here is we have used decision tree classifier, which is fitted onto our data set, and the fitted model is used to check the feature importances. So this function is already built in the classifier, and it will give me the score for every column or feature based on its contribution to the output. So you can see there are different scores for each of the columns. If we see this column has the least contribution to the output. And this column, if you will check, this is the density column. Now what we can try is we can try removing this column from our data set and then try training the model based on this new data set if the accuracy improves or not. So I just remove this density column using the .drop command, and then if you just see the dataset.info, you'll see that the density column has been removed. So this is just for validation purposes. Now once the density column is removed, we can just run the whole training process to see if the accuracy is improved or not. So if you see, the accuracy with our new dataset is 90.48%. which was before 90.7. So we have seen by removing the column named density, the accuracy is not improved. That means removing this column doesn't have much impact on improving the performance of a model. So we could discard this technique in our particular case and move on to the next and final improvement technique, which is the hyperparameter tuning. In hyperparameter tuning, we use built-in method from the sklearn library to search for the optimum value of the hyperparameter, which will give us the best performance of our model. So here we have used randomized search CV, which is the built-in method. It randomly searches for the hyperparameter in the given hyperparameter space. In order to facilitate the whole process, I have created a class called random search, and it contains the method called random search, which again uses the built-in method, which intakes the model, which is the logistic regression model in our case, the hyperparameter space, which we would provide in some time, the random state, which would give us the same output value every time I run this cell, the number of iteration, after which the optimization should stop searching for the optimum hyperparameters, and the scoring criteria based on which the performance of the model would be calculated. So here we have used the accuracy as our performance matrix. The another function that this class contains is best model predict. So it will just search for that particular optimum value using the random search method that I have already explained, and then it will give me the predicted value based on the test dataset provided to it. Now if I just run the class, so the class has been defined. Now in order to use that class, we need to define the hyperparameter space for it. So we use two hyperparameters for our logistic regression. First is the penalty, and the second is the regularization term C. So the penalty contains the type of penalty or regularization that the model should have. So in penalty, we have L1, L2, and none. So these three defines the three types of regularization that the model could have. Then we have the regularization weightage, which is the C, and we have created the values based on the uniform distribution, which is mean at 0 value and with a scale of 10. So we create this hyperparameter space using our dictionary. So once we create the hyperparameter space, we can move on and run the random search function from our class. And now it will try to fit the parameters which would optimize the performance of our model based on the given performance metrics. And it will take some time.
A few moments later.
Okay, so now we have our results for the optimum hyperparameters. The value of C that we got is 4.72 as optimum, and the type of penalty that is optimum would be L2 type of regularization. The best value that we could achieve on our training dataset is 0.877. Now if we check the accuracy of our trained dataset on the test data, we could see that the accuracy that it has achieved is 89.32%. But if we compare it with the last best accuracy that we had, which was 90.7%, it has been reduced. But why is that so? Now I'd like you all to chip in and see what could be the reasons for this. And do comment your answers in the comment section of the video. I would really appreciate that. So that's it for the second part of the video on our series on logistic regression implementation in Python. If you find it helpful, please don't forget to hit the like button and subscribe for more such videos. Thank you for watching.